For this one, two 1 gram spheres are charged equally and placed 2 centimeters apart. When released, they begin to accelerate at, is that 22.5 or 225? 225 meters per second squared. The mass is 1 gram. What is the magnitude of the charge on each sphere? So we know F equals ma, right? We also know that F is equal to K Q1 Q2 over R squared. And we know they're placed, we know that R is 2 centimeters. Okay. So from that, and we know that they said equally charged, so that just becomes K Q squared over R squared. Therefore, we get MA equals K Q, okay, that was weird. K Q squared over R squared. So we get Q is equal to the square root of MAR squared over K. And now plug and chug. So let's see. 0.001 is going to give us 0.225.
Wait,
Yes,
why is M only 1 gram and not 2 grams?
because it's the force of one on the other. Because each one experiences its own 225, right? In one direction. Like we're doing the force of one on the other.
What does it look like when you let go then?
They both move at the same time separately, but it's like yeah, if you let them go, pew, they both take off that way. But then what we're doing is kind of like looking as if the effect of one on, what's the effect of the one on the other? Yeah. Questions? Okay, good. I like it. People are asking questions. What if they're two different masses? Then, well, because of Newton's law, would their accelerations be different? Could their accelerations be different? Because Newton's law says, third law, right? Action, reaction, so their accelerations would have to be the same? No, not the acceleration. Sorry, I was trying to be tricky. What should be the same? The force. So the force on both will be the same, but the accelerations will be different. So if one was double the mass, it would have half the acceleration. Good question. Yes? I thought it was going away. Because if they're charged equally, yeah. Yeah, no worries. That's fine. Ask the questions. Yes.
So in that case, A would be different, but would Q's be the same still? Even
Yeah,
if the mass is
yeah.
different? Okay.
Yeah. Q could be the same because Q is independent of mass. I mean, you could add literally billions of electrons, billions and billions, billions of billions, and you still would not change the mass. Because remember, an electron's 911 times 10 to the minus 31. So even if you added 1 times 10 to the 20 electrons and all the charge that is concomitant, and that is a lot of charge. Because if you add that many electrons, you're adding almost, what, 2 coulombs of charge? And that is huge. That's a lot. But you wouldn't even add a gram. You would add one 10 billionth of a gram. So,
What's a coulomb in context?
what is that number?
6.24 times 10 to the 10.
Yeah,
18.
it sounds completely arbitrary because it's based on a weird system. Because, and I think I mentioned this yesterday, it's all based on galvanic plating. So you determined a coulomb because an object gained a certain amount of mass in a certain time. So that indicated exactly how much current was passing through the system. So you knew exactly how many charges were passing through the system.
What's like, I get that, but like, in the material natural world, what does like 1 coulomb look like?
Okay, I'm gonna pause this. Okay, this actually is gonna be good. We have two 1 gram spheres that are 2 centimeters apart. 1 gram is about the weight of a paperclip, right? 225 meters per second acceleration. Okay, that is like, what is that, like 20 times, 20 Gs? And remember, humans at like 6 Gs pass out. And at 10 Gs, 9 Gs, you die. Because it pulls all the blood to one side of your body. Yeah,
What is 1 G? I don't know how that's meant.
1 G means multiplied by gravity.
Oh,
So like, if I turn a corner and I have like a little mass hanging at 1 G, what angle should it make to the ground? If I'm turning with 1 G? 45, right? Because down is 1 G and this way is 1 G. So if that little thing goes up such that I'm at 7 or 8 Gs, then the blood will go from one side of my head to the other and I'll pass out. And that's like, let's say 10, right? Because humans have experienced up to like 9 and 10 with suits, with special suits. Okay, this thing is 20 Gs, and that's with 100 nanocoulombs. So if you put 1 coulomb of charge on each of these, do the math. Right? This becomes 1 and 1. This is 9 times 10 to the 9th. Right? So you've got 9 times 10 to the 9th, and then let's have some fun here because this is 0.0, this is 4 times 10 to the minus 4. So that becomes to the 13th, 9, 4, let's say 2, just to be friends. You've got 2, 9th, 11th, 200 billion newtons of force on these 1 gram balls. So if I took 2 paper clips and I had 1 Newton or 1 coulomb of charge on each paper clip, and they were 2 centimeters away, and I let them go, they would exert 100 billion newtons of force, right? And if you do the math, like, that's almost like gonna hit light speed. That's how big a newton, or one coulomb of charge. And that's why charges, we move things around, like you can bend water, you can like have balloons stick, and you can do all this crazy stuff. You can have all your hair stand up with like nanocoulombs, millicoulombs.
was that ever existed? Like 44?
Yeah, there are giant capacitors for different things that hold like coulombs of charge. And we'll probably see one when we get into the magnetic stuff, and we'll see how to shrink a quarter.
Shrink a quarter.
Yeah, you can turn a quarter into the size of a dime.
Are we gonna actually do that?
No, we're not gonna do that, because I don't have about $30,000 to build that apparatus.